Okay, this is chapter 6, the trigonometric functions. This is actually the first trig chapter for the college trig course. You may need to review sections 1.1 and 1.2 and chapter 2 of the algebra portion of pre-calculus. So section 6.1 is the trigonometric functions of acute angles. Remember, acute means that it's between 0 degrees and 90 degrees. So the trigonometric ratios. Remember, ratio is really just a fraction. Okay, we look at what is considered the historical or traditional method of defining the trigonometric functions, or just simply trig functions. Okay, we're just going to say trig functions. You may also hear them referred to as the circular trig functions. Later on, we'll see why that name is applied. So the historical approach is also called the right angle trig or right triangle trig, which always means we're going to draw a triangle that has a right angle in it. So we may have to review the Pythagorean theorem. So later in the chapter, we'll look at what is considered the modern approach to the trig functions. So first we need some definitions. So some definitions, terminology, and a notation. It's standard definition, terminology, notation. Nothing weird about it. So definition. An acute angle is an angle whose measure is between 0 degrees and 90 degrees. The measure of an acute angle cannot equal either 0 degrees or 90 degrees. So a right angle is an angle whose measure is 90 degrees. An obtuse angle is an angle whose measure is between 90 degrees and 180 degrees. The measure of an obtuse angle cannot equal either 90 degrees or 180 degrees. A right triangle is a triangle in which one of the angles is a right angle. Since the sum of the three angles of any triangle is 180 degrees, the other two angles of a right triangle are acute angles. Angles are typically named by lowercase Greek letters. Like alpha looks like a funny looking A. Beta looks like a funny looking B, and then gamma, which some people say looks like a fish standing on its head. Theta looks like a circle with a line through it. Theta is probably the most common one. And then please be aware that the way Greek letters printed by machine is not always the way it is written by hand. We have a similar situation with some of our letters. Like the way a printed lowercase g looks like this is not always the way we write it, and the same thing with a lowercase f. So, right triangles. We let triangle ABC be a right triangle. We denote triangle ABC by this thing, that thing that looks like a triangle. You may recall this from high school geometry, so triangle ABC. We let C correspond to the right angle, and we label one of the acute angles theta. So we let the length of the hypotenuse of the right triangle, we're going to denote it by HYP as an hypotenuse. So that's the length of the hypotenuse. We let the length of the side adjacent to angle theta be labeled ADJ, as in adjacent. Again, that's the length. And we let the length of the side opposite from angle theta be labeled OPP. That's its length. So HYP, ADJ, and OPP are lengths of sides of a right triangle. Okay. If you're not in the classroom, clearly you don't see it on the board. So here's our right triangle. Here's our right angle at vertex C. Here's our angle theta. The line segment AB is the hypotenuse that has length HYP. This side is adjacent to theta because it forms one of the sides of that angle. It has length ADJ. And this side is opposite theta. Notice it does not touch the angle, so it has length OPP. This is the standard way of labeling the triangle. Okay, so with this sketch of the right triangle, we're now ready to give the definition of the 6 trig functions of theta. Right now, there are only 6 trig functions. At one time, there used to be a lot more, but 6 is what we've come down to, and it turns out we only need 3 of them, and we can usually get away with just 2. So, definition. Let theta be one of the acute angles of a right triangle. Let the length of the hypotenuse of the right triangle be HYP. And let the length of the side adjacent to theta be ADJ. And let the length of the side opposite from theta be OPP. Okay, so it's that picture. Again, going back, it's that picture. So now we have the following 6 trig functions of theta. The sine of theta, denoted by SIN, and read it as sine theta, not sin. On most calculators now, they'll put the argument, the angle, they'll put it in parentheses. It's to make it clear what you're taking the sine of. Okay, so sine theta, or like this, it's given by sine of theta is equal to opposite over hypotenuse. So it's the length of the opposite side divided by the length of that hypotenuse. Cosine of theta, denoted by cos, cosine theta, is given by cosine of theta as the adjacent over the hypotenuse. Remember, the hypotenuse is the longest side of the triangle, so sine of theta and cosine theta are always less than 1. The tangent of theta, denoted by tan, tangent of theta, is given by tangent theta as the opposite over the adjacent. And notice in the triangle, the opposite and adjacent, we don't really know which is longer. They can in fact be equal to each other. So the tangent of theta can be just about any real number. Number 4, the cotangent of theta is denoted by COT, is given by cotangent of theta is adjacent over opposite. Number 5, the secant of theta, denoted by SEC, secant of theta, is given by secant of theta as the hypotenuse over the adjacent. Now again, remember, the hypotenuse is the longest side of the triangle, so the secant of theta is always greater than 1. And we will see cases when they can't equal, so technically we should say greater than or equal to, just like sine and cosine, we should say less than or equal to 1. And lastly, number 6, the cosecant of theta, denoted by CSC. You will see some books write COSEC, but CSC is more common. Cosecant of theta is given by hypotenuse over opposite. Okay. So those are the 6 trig functions of theta. If you look at them very carefully, you will notice the relationship between the first 3 and the last 3. And that is a relationship that you should learn. So it's the terminology, notation, and conventions. Notice that 3 of the trig functions are the other 3 with co in front of them. Sine, cosine, tangent, cotangent, secant, cosecant. For this reason, we have the following co-function pairs. Sine and cosine are co-functions of each other. Now, if you have co in front of the cosine, you have co-cosine, the 2 co's wipe each other out in the back to side. Tangent and cotangent are co-functions of each other. And lastly, secant and cosecant are co-functions of each other. So these are the co-function pairs. You're going to notice that with the trig functions, a lot of things occur in pairs, or else it's true for all 6, or it's true for 2 of them, or just 4 of them. It's never half and half. If you look very closely again at the definitions of the following, you'll get the reciprocal functions. Okay? So if you look at the definitions, you might have noticed some reciprocal. Remember, reciprocal of x is 1 over x. Kind of like you flip it over. So sine and cosecant are reciprocals of each other. Cosine and secant are reciprocals of each other. And lastly, tangent and cotangent are reciprocals of each other. Now, oddly enough, tangent and cotangent are the only ones that are reciprocals as well as being co-functions of each other. It's kind of like if we had to do it all over again, we might have different names for our 6 trig functions. The reciprocal functions are usually stated like this. Cosecant of theta is 1 over the sine of theta, and sine of theta is 1 over cosecant of theta. Again, since most of these are going to be fractions, remember ratios are fractions, if you just simply write it as 1 over, you might end up with a complex fraction. Secant of theta is 1 over cosine theta, and cosine theta is 1 over cosecant of theta. Again, remember, just flip them over. Just flip them over if you're doing it mathematically. And lastly, cotangent of theta is 1 over the tangent of theta, and we also write tangent of theta is 1 over cotangent of theta. Because of the reciprocal function relationships, the values of the 6 trig functions are normally presented in the following format. You have sine, cosine, and tangent on the left, and cosecant, secant, and cotangent all on the right. Remember, in order to get from the sine to the cosecant, you simply flip it over. Like if the sine of theta is 2/3, the cosecant of theta would be 3/2. Similarly, if the cosine of theta was 1/4, the secant of theta would be 4. And if the tangent of theta like 1/19, the cotangent would be 19. Now, because of the trig functions having been around for forever, we will sometimes forget to say the argument of the function. Like instead of saying sine of theta, we'll just say sine. But remember, you have to take the sine of something. You can't just have little old sine sitting out there doing nothing. So again, the three functions on the right are the reciprocal of the three functions on the left. You can also get the other way around. The three functions on the left are the reciprocal of the ones on the left. The trig functions are also called, again, the circular functions, as in a circle. If you take enough math, you will discover there are functions called the hyperbolic functions, the parabolic functions, the elliptical functions. When speaking about something that applies to all six trig functions of theta, we will simply write this, trig of theta, where trig can be any one of the six trig functions. It's to save us a lot of writing. Since the trig functions have their own abbreviations, if there is no ambiguity, it is not necessary to enclose their arguments in parentheses. However, it's good practice to do so. Like when you write f of x, you put the of x in parentheses. So that means that trig of theta is the same thing as this, trig, but we still say of theta, so trig of theta. Some examples. Using the right triangle below, find the exact value of the six trig function of theta. Simplify your answers. Do not use mixed numbers and decimals in your answers. Okay, unless there's some sort of specific application, we usually don't use mixed numbers or decimals. Okay, so here's my right angle. I've labeled all three of the sides. And here's my angle theta. Okay, remember, hypotenuse, HYP is 37. Adjacent is 35. OPP is 12. Okay, now, be aware of where we put theta. I mean, theta could be up here. Notice the hypotenuse wouldn't change, but ADJ and OPP would switch. So using this, sine of theta, remember, is opposite over hypotenuse. So it's going to be 12 over 37. And it's reduced. Cosine of theta is supposed to be the adjacent over the hypotenuse. So it's going to be 35 over 37. And the tangent of theta is supposed to be opposite over adjacent. So 12 over 35. And it's also reduced. Okay, now to get these three over here, you don't really need to go back to the triangle. You can, but you don't really need to. Remember, to get these three on the right, simply flip those three over. Now be sure you put them in correct order. So we have cosecant of theta. It's going to be 37/12. Cosine of theta, secant of theta, flip over the cosine. You're going to have 37 over 35. And the tangent of theta is going to be flipped over to give us cotangent is 35 over 12. And there are six trig functions of theta. Again, using the right triangle below, find the exact values of the six trig functions of theta, simplify, no mixed numbers or decimals. Okay, notice on this one, theta is sitting up here, but we don't have the length of the hypotenuse. So we must find HYP. So Pythagorean theorem. So 7 squared plus 10 squared is HYP squared. So 49 plus 100 is HYP squared. So 149 is HYP squared. You take the square roots. Okay, 149 is not a perfect square. So HYP is this god-awful number, square root of 149. And so for theta, opposite is 10, adjacent is 7. So again, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then these three, flip those three over. Myself, personally, I don't care if you rationalize the denominator or not. In certain historical cases, we still do. And that's only because of history. Because notice if you rationalize these denominators, if you flip them over, you got to undo what you did. So it's like you spend half your life rationalizing denominators for really no good reason. Okay, suppose that theta is an acute angle with cosine of theta equal 2 seconds. Find the exact values of all six trig functions of theta. Simplify. Now notice you got to get at least one right because you're told the cosine of theta. So we got to find sine, tangent, cosecant, secant, and cotangent. Notice you can get cosecant would be 7/2. So we draw a right triangle, like one of the acute angles theta, and use the given trig function to find the lengths of the two sides of the triangle, and the Pythagorean theorem will give us the length of the other. As you remember, cosine is adjacent over hypotenuse. So cosine is 2/7. Cosine is adjacent over hypotenuse. So ADJ is 2, HYP is 7. Okay, you have the triangle on the board, but you clearly don't have the board in front of you. So from Pythagoras, 2 squared plus opposite squared is 7 squared, right? So 4 plus opposite squared is 49. Opposite squared is 45. Take the square root. You get square root of 45, which remember 45 is 9 times 5. So you get 3 times the square root of 5. Okay, we now have everything we need. Remember, the sine is opposite over hypotenuse. So it'll be 3 square root of 5 over 7. Tangent, or cosine, just to get it there, given to us 2/7. Tangent is opposite over adjacent. So 3 square root of 5 over 2. And then get the other 3, flip those 3 over. So opposite over hypotenuse, given, opposite over adjacent, flip the sine over, flip the cosine over, flip the tangent. Again, I am not rationalizing your numbers. If you want to, go ahead, have a ball, but I see no need for it. Special angles. And these are the same special angles you saw in high school geometry. So we're going to get the exact values of sine, cosine, and tangent for some of the special angles. Notice we usually pick on sine, cosine, and tangent because to get the other 3, we flip those 3 over. And if you're really good, all you need is sine and cosine because tangent can be found from those 2. So the values come from special triangles from high school geometry. Again, remember them, the 30, 60, 90, and the 45, 45, 90 triangles. So the 45, 45, 90 triangle. Sometimes referred to as an isosceles right triangle. So consider a triangle whose acute angles both measure 45 degrees. Since both of the acute angles are the same measure, the 2 legs will have the same length. For convenience, we let this length be 1. So we find the length of the hypotenuse. So it's going to be leg squared plus leg squared is hypotenuse squared. So 1 squared plus 1 squared is hypotenuse squared. We get 1 plus 1. 2 is the hypotenuse squared. So the hypotenuse is the square root of 2. And again, just leave it square root of 2. We're not trying to approximate. Remember, we're trying to get the exact values. So there's our triangle. 45, 45, there's our right angle. 1, 1, that should say square root of 2, not 2. So that should say square root of 2, not 2. So for the 45 point triangle, no matter which 45 angle you pick, you're going to have opposite is 1, adjacent is 1, and hypotenuse is the square root of 2. So for purely historical reasons, we still rationalize the boundaries of the trig functions for special angles. Okay, it's just for purely historical reasons. So the sine of 45, remember, it's opposite over square root of 2, so 1 over square root of 2. If we rationalize, you get root 2 over 2, which is about 0.707. Okay, the cosine of 45 degrees is adjacent over hypotenuse, so the same thing. 1 over the square root of 2, which will be the square root of 2 over 2, which is again is about 0.707. Now remember, the tangent of 45 degrees will be opposite over adjacent. 1 over 1, which is 1. And there's no need to approximate that. Remember, to get these 3, flip those 3 over. And it's easier if you flip over the ones that have not been rationalized. So the cosecant of 45 degrees would be the square root of 2, which is about 1.414. The cosine of 45 degrees is also the square root of 2, which is still 1.4142. And the cotangent of 45 degrees is 1. And yes, you really should commit those to memory, but you can always use your calculator. And if you have a really powerful calculator, like the I think TI-89 or the TI-92 or the TI-Inspire, they will give you these exact values. So you must learn these, you personally. So the 30, 60, 90 triangle. So that means we'll be learning the special angles of 30 degrees and 60 degrees. So to find the lengths of opposite, adjacent, and hypotenuse for a 30, 60, 90 triangle, we're going to start with an equilateral triangle. So that means all angles are 60 and all sides have the same length. And we're going to have, for convenience, we're going to let the length of each side be 2. 2 inches, 2 whatever. So all of them are 60 and all the lengths are 2, 2, and 2. Again, many of you, hopefully all of you, recall this from high school geometry. Okay, so we cut this triangle in half by drawing an altitude of length A from the top vertex. So that is length A. Remember, you now are going to see why we picked 2. We cut this in half. So if this whole length was 2, that length from here to here is just 1. We're going to take a look at the right half triangle, so this one over here. Okay. Remember, if this angle was 60 and we cut that one in half, that should be 30. And also remember, for a right triangle, the 2 acute angles should add up to 9. We have to find the length of A, the length of that altitude. And of course, we can use the Pythagorean theorem. We're going to have a squared plus 1 squared is 2 squared. A squared plus 1 is 4. A squared is 3. So A would be the square root of 3. So now we go back and label all 3 sides of the triangle. Notice from this one triangle, we can then find the trig functions for 30 degrees and the trig functions for 60 degrees. It doesn't matter which one we do first, you got to do them both, and you got to learn both of them. And notice, since they come from the same triangle, please don't confuse them. So for the 30 degrees, remember, its opposite will be 1. Its adjacent will be the square root of 3. And of course, the hypotenuse will be 2. So opposite is 1, adjacent is square root of 3, hypotenuse is 2. We're now ready to do the trig functions. So the sine of 30 degrees, 1/2. Okay, the cosine of 30 degrees should be square root of 3 over 2. And the tangent of 30 degrees will be 1 over the square root of 3. Well, if we're going to approximate cosine at 30 degrees, about 0.8660. Okay, so tangent is 1 over the square root of 3, which again we rationalize it as the square root of 3 over 3, which is about 0.5774. And to get these 3 over here, flip them over. So the cosecant of 30 degrees will be 2. The secant of 30 degrees will be 2 over the square root of 3, which again we rationalize as 2 square root of 3 over 3, which is about 1.1547. And the tangent of 30 degrees would be the square root of 3, which is about 1.732. And again, we do those. And if all else fails, since you saw how we derived them, you can always draw the 30, 60, 90 triangle. Okay, for the 60 degrees, okay, 60 degrees is down here. Okay, its opposite is the square root of 3. Its adjacent is 1. And the hypotenuse is still 2. Okay, so now we're ready to find the 6th trig function. Remember, the sine of theta will be opposite of hypotenuse, square root of 3 over 2. That should be a 1, not a 2. It's really a 1. No, I'll fix that, didn't I? So, well, let me go back to the reason I did that. Then the sine would be the square root of 3 over 2. The cosine of 60 degrees would be 1/2. Okay, and then the tangent of 60 degrees would be the square root of 3. Okay, so square root of 3 over 2, which we saw earlier, is about 0.8660. The cosine of 60 degrees would be 1/2, which hopefully you know is 0.5. And then the tangent of 60 degrees would be the square root of 3, which we saw an approximation for it earlier. Now to get these 3, flip those 3 over. So the cosecant of 60 degrees would be 2 over the square root of 3, which is 2 square root of 3 over 3. And we saw its approximation before. Secant of 60 degrees would be 2. And the tangent of, the cotangent of 60 degrees would be 1 over the square root of 3, which is root 3 over 3, which is about 0.5774. Again, the trig functions for 30 degrees and 60 degrees look very much alike. And that's because, remember, they both came from that same triangle, the 30, 60, 90 triangle. And again, you must learn these. So the trig functions of any acute angle. Okay, we're still looking at acute angles. Now, again, remember, acute is between 0 degrees and 90 degrees. It will basically come down to using a calculator. You must be sure that your calculator is in degree mode. Now, again, everything that we're doing here is geared toward the TI-8384 family of calculators. Most of the TI calculators are very similar, but if you get one that's too fancy, you're kind of on your own. So degrees, minutes, and seconds. We're going to look at I'm going to look at smaller divisions of a degree. It is important that you know the symbolization of the smaller units of a degree. I hope you know the degree symbol is that little open circle. So a minute is 1/60th of a degree. So there are 60 minutes in a degree. It's kind of like time, 60 minutes in an hour. 1 minute is symbolized as this, one with what looks like a little apostrophe. A second is 1/60th of a minute. So there are 60 seconds in 1 minute. Again, like time. So since there are 60 minutes in a degree and 60 seconds in a minute, there are 60 times 60, or 3,600 seconds in a degree. So a second is rather small. 1 second is symbolized with this, one with what looks like a double apostrophe. So when writing something like 10 degrees, 15 minutes, 12 seconds, we write it like this: 10 degrees, 15 minutes, 12 seconds. Now, there is no smaller unit for after seconds. You would just have a decimal second, like 0.25 seconds or something. On the TI-8384 family of calculators, the symbols for degrees and minutes is located in the angle menu. The angle menu is the second of the apps button. It may take you a while to get used to your calculator if you haven't used these. So pressing the angle button reveals the following screen. So notice that's the degree symbol. That's the minute symbol. For whatever reason, TI chose not to have seconds. It's kind of strange, but so choice number 1 is degrees, and choice number 2 is minutes. To note minutes on TI-83, you must press the following keys. Okay? If you're going to give stuff to your calculator, you may as well learn how to use it. So you're going to use alpha plus after you enter the number. The keystrokes to enter 10 degrees, 15 minutes, 12 seconds. Okay, here are your keystrokes. 10 for the 10 degrees, second angle, because remember, second of apps is angle. And you're going to enter 15, so you're using that, second, and then you're going to do the angle apps button again, and then 2 for the minutes. No, excuse me, 2 for that symbol. And then 12 alpha plus, and you get something that looks like this. So just so we can see it, let me take out my TI-84. So if we follow it, what's we're going to do 10, second, apps. Go ahead and press enter for the degree symbol, because notice it's already there. And notice you have 10 degrees. Then 15, second, apps. Now you want the minutes. So choice 2. Or if you want, you can scroll down to it. And then the 12 seconds. 12 alpha plus. Because notice in green, do you see that little double apostrophe looking thing for the second? So since it's in green, we press the alpha. It's in green. I believe on the 83 it's in orange. Okay. Just check, let me see. Yeah, and it's actually it's in green as well, different shade of green. So you would do 10 second angle, 10 degrees, 15 minutes. If you want, you can scroll down to it. And 12 alpha plus 6. There you go. Let me clear that crap out. And I click that one. And try that one out. And I'm going to just clear it. Okay. If you do enough trig, you'll get used to these weird things. Okay? So we're dividing trig functions on the TI 8384. Probably should have kept one of them open. So notice that the calculator keypad has sine, cosine, and tangent. The calculator can evaluate these directly with no additional keystrokes from you. Okay, to do the other three, you have to remember that cosecant is 1 over sine. Secant is 1 over cosine, and cotangent is 1 over tangent. That's the reciprocal relationships. And I guess let me bring back the TI. And let me make sure I'm in the correct mode. So mode, and I am not in degrees. So I scroll down, go over 2 degrees, press enter. I'm now in degree mode. So cosecant theta is going to be 1 over sine theta, secant theta 1 over cosine theta, and cotangent theta 1 over tangent theta. And you must write them this way, 1 over. So, like the following, round the final 6th place, you are the best of 5. Okay, if we want to, we can set your float to 6. So let me go up to float, or you can do the rounding yourself. So let me float over to 6, press enter. Now, if I wanted to do sine 12 degrees, sine, and notice the calculator opened the parentheses. I don't think the 83 does that. Let me check. I'm not sure I'm in the right mode. I'm not. Okay. Well, let me float it over to 6. Remember, if you do this on your calculator, until you change it, it'll stay that way. And so it's if I do sine, oh, it opens parentheses as well, 12 degrees. Now, if you wanted to be safe, you could put the degree symbol, but you know, it's easier to just put it in mode. So, 0.207, 902, let's see if this one gets the same thing. You don't really have to close parentheses. Notice I did here, but I'm not going to here, and you can see what happens. It assumes the parentheses are closed at the end, even if you don't want them there. Then cosine 12 degrees, tangent 12 degrees. Okay, now to get the cosecant, you want 1 divided by the sine of 12 degrees, like that. Cosine, the secant, you want 1 divided by cosine 12 degrees. Okay. And lastly, for the cotangent, you want 1 divided by tangent 12 degrees. Now, notice that ending in a 0. If you don't put the 0, you don't have 6 decimal places. That's sometimes why it's best to let the calculator do all the rounding for you. You may as well let it do all the work for you. If it was really good, they'd take the test for you, wouldn't it? So, I've set my mode to degrees and the float to 6. So this way the calculator will do all the rounding. And I don't need to use the degree symbol, you know, switch to angle and all that other nonsense. Again, if you get really good at the calculator, you might be really fast at it. So since I already did these live and in person, cotangent 22 degrees. You're going to do 1 over tangent 22 degrees. And again, if you want to see it on the calculator, you can clear all that nonsense out. 1 divided by tangent 22. And again, there are the keystrokes, 1 divided by tan, 22, close parenthesis, because remember, the calculator opened, and then press enter. Okay, the cosine of 67 degrees, 17 minutes, 23 seconds. So let's just go ahead and take out Mr. Calculator again. And let me clear out that nonsense. So we got cosine, 67, second angle, the degree symbol, then 17, second angle, the minute symbol, so it's 2, and then 23, alpha, plus, close it, 0.386, 0.17. Okay, I got the same thing. Cosecant of 20 degrees, 16 minutes, 2 seconds. Okay, so you're going to do 1 over sine of 20 degrees, 16 minutes, 2 seconds. And you get 2.886844. Again, if you're a real person in one of my classes, it's a shame to get these wrong because it's just a counter exercise. So, using your calculator may seem trivial, but it is an important skill. Okay, the secant of 33 degrees, 5 minutes, 11 seconds. So remember, it's going to be 1 over cosine of 33 degrees, 5 minutes, 11 seconds. So you get 1.193533. Decimal degrees. The decimal degrees are simply expressing degrees using decimal numbers instead of degrees, minutes, and seconds. Like 12.853 degrees or something like that. So the problem is really just converting between decimal degrees, often abbreviated as DD, decimal degrees, and degrees, minutes, and seconds, often abbreviated DMS, degrees, minutes, seconds. We use the following. Okay, 60 minutes is 1 degree, and 60 seconds is 1 minute. Okay, I find that I can do this quicker using these little conversion factors rather than trying to use the DMS and DD keys on the calculator. So, and 3,600 minutes is, 3,600 seconds is 1 minute. Okay, the TI-8384 angle calculators can convert decimal degrees to degrees, minutes, and seconds using the angle menu. It is choice number 4 that will convert degrees, minutes, and seconds. Unfortunately, the calculator don't have a key to convert degrees, minutes, and seconds to decimal degrees. It just doesn't. Others do, but the 8384 does not. It's another reason to learn how to use the 60 minutes is a degree and 60 seconds is a minute. So, converting decimal degrees to degrees, minutes, and seconds. So it's like you got 12.77 degrees. Okay, so we look at how to do this by hand and how to use the calculator to do it. You can use either method. Personally, I prefer by hand. Okay, so this is kind of abbreviated as decimal degrees going to degrees, minutes, seconds. So method 1, using the calculator. Enter the decimal degrees in the calculator. Go to the angle menu, second angle up. Press choice 4 to make it go to D minutes. And press enter. Method 2 by hand. First you find the number of minutes. Multiply the decimal part of the decimal degrees by 60. So you get like 15 point something. The whole number part is the number of minutes. So like 15 point something, 15 minutes. Subtract the integer part of the result of step 1 from the entire decimal number from step 1. In other words, ignore the decimal part now. Ignore the integer part, just look at the decimal part. So in step 2, you're basically looking at the decimal part from step 1. Okay, what you have left are the decimal minutes. Okay, so now find the number of seconds, multiply the decimal part from step 1, multiply it by 60. The entire result, including decimal part, is the number of seconds. Okay. Convert the following decimal degrees to degrees, minutes, and seconds. If necessary, round any decimal seconds to the nearest tenth of a second. Okay, first one, 18.32 degrees. Okay, method 1, remember that was the calculator. So you're going to key in 18.32 degrees into your calculator and then press the following keys. Second, angle apps for decimal degrees. You get it. And again, if you want to witness it, you can figure this out. So 18.32 second angle, choice 4, enter here. Method 2. Multiply 0.32 by 60. So you're going to get 19.2. So you have 19 minutes. Okay, so we have 19.2 minutes. Subtract off the 19. So you got the 0.2. Multiply the 0.2 by 60. You get 12. So you got 18 degrees, 19 minutes, 12. Just like the first one. Okay, 118.562 degrees. You get 118 degrees, 33 minutes, 43.2 seconds. And again, if you want to see it being done, 118.562. Now, if you're wondering, do I need to put the degree symbol? Because you notice in the first one I didn't. But if you do, I want to go ahead and put it there. And then choice 4 again. Now, if you want to see the other way, I'm going to have 0.562 times 60. Then you get 33.7200. Okay, if you're wondering why I have all these extra zeros, I'm going to set my float to 6. Let me just let float be float. Okay, so I got this 33.72 still, so I've got 33 minutes. Now I'm going to do 0.72 times 60. And that's 43.2 seconds, just like we got here. Okay, 98.605 degrees. You get 98 degrees, 36 minutes, 15 seconds. And then I'm going to do it by hand. So I'm going to have 0.605 times 60. 36 minutes. Then 0.3 times 60. 18 seconds. Oh. What happened? Okay, now again, as far as which method do you use, it's entirely up to you. As long as you get the correct answer, I won't know what you do. Okay, converting degrees, minutes, and seconds to decimal degrees. So we're going the other way. So in the language of the calculator, you're going from DMS to DD. So DMS to DD. So some calculators do have a DMS to DD key, but the TI-8384 family of calculators doesn't. Or if it does, I can't find it. And we can do it by hand just as easily though. So the method for converting degrees, minutes, and seconds to decimal degrees. Again, 60 minutes in a degree, 3,600 seconds in a degree. So the decimal degrees is going to be the degrees plus the minutes divided by 60 plus the seconds divided by 3,600. So that's your decimal degrees. Degrees plus minutes divided by 60 plus seconds divided by 3,600. So convert the following to decimal degrees if necessary around the final answer to 4 places to guard the decimal point. You got 18 degrees, 22 minutes, 45 seconds. So it's going to be 18 plus 22 over 60 plus 45 over 3,600. To 4 places, you're going to go like 3792. And again, if you want to witness it on the calculator, I witness math. 18 plus 22 divided by 60 plus 45 divided by 3,600. And again, if you set your float to 4, it'll do it for you. 300 degrees, 12 minutes, 36 seconds. You're going to have 100 plus 12 over 60 plus 36 over 3,600. And when you crunch that out, you get exactly 100.21 degrees. You need to get in the habit of putting the degree symbol. Later on, when we learn different ways to measure angles, without the degree symbol, it's not degrees, even if you think it is, or want it to be. So cofunctions and complements is the fourth big topic. Recall the following pairs of cofunctions: sine, cosine, secant, cosecant, tangent, cotangent. We'll also recall this. Two angles are called complementary, and that's complementary with an E. If you have an I, it's It's like my lucky today. So the complementary if and only if the sum of the measures is 90 degrees. Each angle is called the complement of the other. So 30 degrees is the complement of 60 degrees, something like that. So if the angle is theta, then its complement is 90 degrees minus theta. Okay, so consider this picture. My angle theta is up here. Hypotenuse is HYP. What's opposite theta is down here. What's adjacent is up here. Remember, this is supposed to be a right triangle. So we're going to add to this picture the second of the other acute angle. The other acute angle is the complement of theta, so it's 90 degrees minus theta. We're going to show it in red. Notice the hypotenuse is the same. So in terms of the 90 degrees minus theta, OPP is up here. ADJ is down here. Notice between theta and its complement, hypotenuse stays the same. It's the adjacent and hypotenuse, that adjacent and opposite, that switch their roles. So notice, the value of HYP is the same for theta and 90 degrees minus theta. The value of OPP for one is the value of ADJ for the other. So in particular, OPP in black is equal to ADJ in red, and ADJ in black is OPP in red. But hopefully no one is too severely colorblind. This is in red. So this gives the following results. The sine of theta is the cosine of 90 degrees minus theta. The cosine of theta is the sine of 90 degrees minus theta. The tangent of theta is the cotangent of 90 degrees minus theta. The secant of theta is equal to the cosecant of 90 degrees minus theta. In general, we have the following. Co-function identities. It's basically going to summarize those four previous things into one. That trig represent any of the six trig functions, and that co-trig represent the co-function of the trig functions given by trig. Then, the trig of theta is the co-trig of 90 degrees minus theta. Now remember, co-co-trig is just trig. We've actually written down something that's part of the next chapter. Okay, remember, there are only 6 trig functions. So it's like if you're having trouble learning those 6 things, you will have a lot of trouble with trig, because that's all there is, just those 6 trig functions. So again, you never write co-cosine. So co-co-trig is just trig. So write an equivalent expression using the cofunctions and complements. Simplify your answers. Use correct names and notation in your answers. Do not evaluate. So resist the temptation to take out your calculator. Okay, the tangent of 34 degrees. Remember, the cofunction will be cotan. You've got to find the complement of 34 degrees. So the tangent of 34 degrees is the cotangent of 90 degrees minus 34 degrees. By simplifying, I mean, don't leave it like this. Actually do the arithmetic. 90 minus 34, you get 56 degrees. Again, don't evaluate it, leave it. Now, just for fun, you can evaluate tangent, evaluate cotangent, and see if you get the same result. Okay, number 2, the cosecant of 72 degrees. The cofunction is going to be secant. The complement will be 90 degrees minus 72 degrees. And 90 degrees minus 72 degrees is what, 18 degrees? That's the end of section 6.1. The next section will be 6.2. Now again, if you're doing like the entire college algebra, college trig class, we basically picked up in chapter 6 for trig, where college algebra ended in chapter 5. I hope this helps you.